Right, we're interested in this part. I'm more interested in this part here, but that comes up a lot. That just means it's a reversible reaction. So the reaction is going both ways. These two join together to form that, and them two join together to form that. Delta H just means change. That is capital D, it stands for delta. It's a capital D for in the Greek alphabet. H is enthalpy or energy, so change in enthalpy is probably a better word rather than using energy or heat energy. Right. Have you noticed it's a negative? That tells you it's an exothermic reaction. Right, so what you do is just say draw a line in the middle, write the reactants here, that's these things. 4NH3 plus 5O2. And because it's exothermic, the energy levels will go down. So at the end of this line here, you go down and draw another line. And it's 4NO plus 6H2O. So we've just drawn the energy level diagram or completed it. We're not interested in that. We're interested in this. This is right. We need to complete this, but I've not copied the other stuff over. So this is an endothermic reaction, first of all. So it might give delta H of plus 36 kilojoules per mole, for example, yeah. That tells me it gains energy from the surroundings. That's what makes it an endothermic reaction. So remember that, endothermic reaction. So this is the energy level of these are the reactants. So the products will have gained energy and move up here. And this gives, right, let's write this down. H2O plus carbon dioxide plus sodium ethanoate, CH3. Oh, come on. Right, you don't worry about this. All I'm interested in you knowing is CH3Q. Right. All I'm interested in you knowing is that the energy level's gone up because it is an endothermic reaction, and that's it. I'm going to forget everything else. Right, we're not really interested in this, but we could do it. Look, you've got 2 hydrogens, 2 hydrogens, 3 oxygens. So if I put I mean, to be honest with you, I could put a 1 there, a 1 there, and half here. Right, that'll balance it out. Or I could put a 2 there, a 2 there, and a 1 there. And I don't need to write the 1. Right, what is a catalyst? You've got to learn this dot for dot. A substance that increases the rate of reaction by providing an alternative reaction route, or route for the reaction route. And we can say and is not used up, or is not used up. Used up. Right, okay, I need to finish this off. By providing an alternative reaction route with a lower activation energy. So this is the full definition. If you learn these 4 points, always just throw them in and it works. Right, I want to show you, look. Can you see this is an energy? No. This is an energy level diagram. Level, level. It's subtly different to, so it took me a while to cotton onto this. A reaction profile. So it goes along, showing you that, goes up, and back down, and then it levels off because the reaction is complete. Right, now we need to show on this diagram, get rid of that, the activation energy, EA. So look, what you do is you draw a line, just clear it, and then from the top to the bottom, draw a line and label it EA, activation energy. On the diagram, draw a curve to represent the reaction profile with a catalyst, and it's always the same. All you do is you're following this along, but this time it goes lower. Can you see? That's the activation energy, but with lower, and just follow it down, and it just finishes there. And you can label that E cat. That's what you'll come across. Yeah. Okay. I'm not interested in that. Right. Right. Okay. We can do this without. It's an exothermic reaction. Lithium iodide into water to form lithium iodide solution. So they've given us everything, but not in an equation. So they've put, look, they put lithium iodide and water here. To form lithium iodide solution. So what you do is, these are the reactants here. It's exothermic, so it's going to lose energy. So we're expecting the products to be down here, and it'll be lithium. Nope. Lithium iodide solution, aqueous. Done. That's it. Right, you don't need to put, this line here. You don't need to connect them two lines. The fact that it's lower has told you that it's exothermic. Right. This is a reaction profile diagram. It's reversible. Here you can tell. And what does that minus tell you? That minus tells you it's lost energy. So therefore it's a what type? Exothermic. Right, I don't know why. That's supposed to be a smooth curve anyway, by the way. Right, okay. On the diagram, draw the reaction profile when a platinum catalyst is used. So what did we say? A catalyst is going to start here, go lower, and then end down here. Draw a line, and then that there will be E, energy change with the catalyst. Yeah, we've done that and done that. Right, that's it. We're not interested in this. This is going to come in a separate video. Right, okay, so look, we've got combustion, complete combustion with methanol. So you've got methanol, it gives carbon dioxide and water, right? Right, do you know when you combust methanol, you give off heat, don't you? Because you see a fire. Right, because you've got heat, it's going to be exothermic. It's going to lose energy. So what they're saying is this here should be down here. First of all, yeah. So the products should be below reactants. Right. And the other one is methanol needs what? Oxygen to combust. So oxygen is missing from where? From reactant side. There you go. Keep moving on. Right, reaction profile diagram. That's okay. Right, what it is you've got carbon monoxide reacting with hydrogen, and it will give CH3 OH. It will give ethanol. Right, so this is an exothermic reaction. That bit of data is missing from here, unfortunately. So what happens is, look, these are the products, CO, H, and H2, carbon monoxide and hydrogen. So the energy, the reaction starting, it's going, and then because it's exothermic, I'm going to draw this line below. Okay, so that's CH3OH. You've got this line here. That there is the activation energy. Right, and the change in enthalpy, was, this is where the enthalpy was, this is where the energy level was, and it's come all the way down to here. Okay, that's the delta H. So we've drawn that, we've drawn activation energy E, we put E for A, we've taken it further. Right, state the effect, if any, of the catalyst on the enthalpy change. Right, really, do you know a catalyst does not affect the energy level? It just affects the rate of reaction. It doesn't affect the yield either. But don't worry about that. Does it have an effect? No, it has none. I'm not worried about that. Right. It's a bond energy one. It is going to be tricky. Right, okay. Let's try to make sense of this. You've got hydrogen. You've got hydrogen, because it's, what is it? It's atomic. It runs around in pairs. So it's got hydrogen to hydrogen bond. Bromine is also diatomic, and it's got bromine to bromine bond. Right, that's that. And then on the other side, you've got hydrogen bromide. So you've got hydrogen bromide. So there's a hydrogen bromine bond. but there's two of these. So this is what we've got really. Right, that's on one side and that's on the other side. Right, how do you work out the enthalpy change, the change in energy, for this sort of reaction? And what you do is you do break minus make. This is how I remember it. Break minus make. So we need to break up everything and then rebuild it. Yeah. So what do we break up? We break up that which is there, and we break up that which is there. So what is a hydrogen to hydrogen bond? It's what? So it's going to be 436 plus bromine to bromine is 193 equals 629. Then we work out make. So we've got hydrogen bromide, hydrogen to bromine, so it's a 366. So that's break, and then now we're going to do make 366, and there's two of them, isn't there? There's one here as well, so that equals 732. Now all we do simply is there another nice color? No, there isn't. So we do that, take away that, break minus make. So we do 629, take away 732. It's going to give a negative number, so it'll be minus 103. Now what does this minus indicate? That it's what? Exothermic. It's an exothermic reaction. Right, break. The lesson from this is break minus make is the change in enthalpy, delta H. Break minus make, break minus make. Alphabetical order, B and M. B and M. Let's go do some shopping. No, maybe not. I'd rather go to Waitrose. There's no roses in Bradford. Right, that is plain. No, can't be doing that. Right, what we're doing? I'm losing the plot. Right, okay. They're talking about energy. All we're interested in is this. You've got that. You're going to react it with that, and you're going to get this and this. So we need to break these, and we need to make these. And then all we do is B and M. Break minus make, alphabetical order. Right, so they've been very kind and they've drawn this for us. Look, they've got 1 nitrogen hydrogen, 2 nitrogen hydrogen, 3 nitrogen hydrogen, 4 nitrogen hydrogen. So we have got 4 times that's a good question. Where's nitrogen hydrogen bond? Oh, there you go. This is a bit awkward. Right, okay, no problem. So what we're going to do is we're going to write 4 times nitrogen hydrogen bond is 391. Yeah. Now go back up, and I'm going to look at this nitrogen to nitrogen bond. There's 1 nitrogen to nitrogen bond. So I've got 1 times nitrogen to nitrogen bond is 159. Right, that's that done. Now if you look carefully, we've got 1 oxygen hydrogen, 2 oxygen hydrogen, 3 oxygen hydrogen, 4 oxygen hydrogen bonds. So we've got 4 times oxygen hydrogen bond is 436. No, 463. 463. Too late for me in the day. Right, the last one, right, we've got an oxygen-oxygen bond and another oxygen and oxygen bond. We have 2 oxygen. We have 2 times oxygen-oxygen bonds are 143. So all we've done is gone through all those. If you add those up, you should get 3861 kilojoules. Right? So this is break. And on this side, we have got make. And there's only 2 types of bonds, so let's have a look. They've laid it out for us here again. We have got a double nitrogen-nitrogen bond, only one of them. So what we do is we do 1 times nitrogen-nitrogen is 945. And then the rest are, can get away with this color, right? Hydrogen, oxygen, 1, 2, 3, 4, 5, 6, 7, 8. So we've got 8. 8 times oxygen hydrogen bond is 463. Now if you add these up, you get 4649. That's according to the mark scheme. Right, what did we say? How do we work it out? Break minus make. And if you subtract them two, you should calculate the enthalpy change. Right, you should get oh, I'm trying to figure out what the right, okay, let's work it out. 4649 minus 3861, it's an 8. 5168 317 788. We've got 788 positive. So it's, what type of reaction are we expecting that to be? We're expecting that to be endothermic. Let me have a check. Yep, that's it. Right, okay, good. Now we're doing the same thing here. So it's been presented slightly differently. So they've actually shown the bonds, which is good. So look, that's the middle point. So you've got break minus make to give you the enthalpy change, delta H, yeah? So look, we've got CH, CH, CH. We've got 3 times CH, and CH is 412. Now we've got OH, we've got 1 times OH is there. And then we've got CO bond, a CO bond. So we've got 1 times CO is 360. Right. We should get, no, we've not finished yet. Got that, got that, got that. Let's, right, we've got double O bond. And we've got 1.5 of these, so we have to do 1, 1, 1. Let me get that right. 1.5 times an OO bond is 496. 496. If you add these, you should get T2803. Now we're looking at the make. So we've got a CO and a CO. So we've got two lots of CO is that one, so it's 743, and we've got, right, we've got to be careful with that. We've got a OH bond, we've got two of them, so we've got 2 times OH. What is OH? Yeah, they've given it 463, right? But we've got two lots of that here. Can you see that there? That 2 there. We've got to be careful. So we have to multiply everything by 2. And when you do that, you should get 3338. And we said it's break minus make. So we just subtract the two numbers. So it's 2803 minus 338 should give 2. What does it give? Let's have a look. Enthalpy change. It should be minus 535. Yeah. Right. What does this minus indicate to you? That it's what? Exothermic. It's lost heat to the surroundings, so it's lost energy, minus. Right, okay, come on, let's keep going. Same thing here. We're not interested in this. We're not interested in that. Although you do know this because it's your fifth acid. It's phosphoric acid, H3PO4. 300 degrees C, and if you add them two, you get 60 to 70 atmospheric pressure. Right, look at this. We've got 1 CH, 2 CH, 3 CH, 4 CH, 5 CHs. We've got 5 times CH is that 412. Then we've got OH, got 1 times OH is 463. Then we've got CC, only 1 CC. 1 times CC, CC is there, carbon to carbon is 348. And then finally on this side we've got a CO. So we've got 1 times CO is 360. If you add all these together, you should get 412 CHO. Let me check that. Yeah, it's gonna be 3231. There's another way of doing it. I'll try to explain that in a bit. So we've got a carbon to carbon double bond. So it's one of these, which is 612. Then you've got 1, 2, 3, 4 times CH, where CH is 412. And then you've got OH. You've got 2 times OH is 463. Right, this is 3186. So this is break and this is make. So what did we say in alphabetical order? Break minus make is 2, 3, 2, 3, 1 minus 3186, and you get 2086, 3045, and it's a negative, it's a minus 45. Okay, what does the minus indicate to you? This negative answer? It's what? Exothermic. There's another way of doing it. You can say, look, we didn't break 1, 2, 3, 4 carbon hydrogen bonds, so we can get rid of them. So only the ones that are colored were broken and remade. Right, I think that's the last question. Right. So what they've done is they've broken it up for us. But you've got to be careful. You've got 3 oxygen-oxygen bonds. So you've got 3 of these. And you've got 2 lots of these. And you've got 3 lots of these. Oh, 3 lots of these. So this is going to require a bit of so let's look at this slowly. So we've got carbon, hydrogen, 1, 2, 3, 4. So we're going to start here. We've got 4 times carbon, hydrogen. Carbon, hydrogen is 412. Then we're going to add oxygen, hydrogen. 1 oxygen, hydrogen is that one. 1 times 4, 6, 3. Then we're going to add a carbon, oxygen. We're going to add a carbon, oxygen, which is 360. Then we're going to finish off with carbon, carbon. 1 times carbon, carbon is 348. Oh, we've not finished yet. I'm too eager, too eager. Right, now we've got here a oxygen, 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 oxygen is there, and it's gonna be 496. So we've got 1 times 496, but we've got to be careful because we've got 3 lots of that. So it's times 3. Now we're done on this side. If we add all them, we should get 4719. So this is break. Now we need to go on to make. So we've got a carbon, oxygen, carbon, oxygen. Carbon, oxygen is there. So it's 3. So we start here, we'll say 3, no, 7, 4, 3. We've got 2 of them. But careful, we've got 2 lots of those, right? So we multiply everything by 2. Right, let's do this one. Hydrogen, oxygen, hydrogen, oxygen. Where's hydrogen? Oxygen is there. 4, 6, 3. So we've got 2 lots of 4, 6, 3. But again, can you see we've got 3 lots of that going on? So we multiply everything by 3. So if we add all those, we should get 5750. This is make. Okay, this is the product side make. So all we do is in alphabetical order: break minus make, B&M stores for shopping. Break 4719 minus 5750 gives a total of minus 1031. Right, what does that minus tell you? It tells you that, what did it tell you actually? Oh, it's exothermic. Hey, that is done, that is finished. We are fantastic. I'm so tired, I have to scroll to the top just to relieve that. Yay, that is fake. It is the 16th today. Someone has put a fake. Oh, whoa, no, 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 no. No, 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 no. Oh, no, 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 no. Did you see that? Invisible ink. Anyway, what? Whoa, what's going on? What's happened? Don't know what's happened. Anyway, that was weird. We're done. I don't know why I'm babbling on for, but we're done. Well done.